Hello, today we are going to look at the numeral systems with base 10 to 8 and 16. This is an important topic for programming, but also for networking and for computers in general. I have searched on Google for the wiki article. Radix is a synonym for base in the various numeral systems which exist. There's the one that we use, which is the Hindu-Arabic base 10 with digits from 0 through 9. So inclusive 0, inclusive 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is base 2, base 10, and the other numeral systems with base non-10, which we're going to look at, are base 2, 8, and 16. This is the Wikipedia page in the simple English language. Let's look first at the digits for each of these numeric systems. So there's base 10, which has 10 digits, 0 through 9. Base 2, which has 2 digits, 0 and 1. Base 8, 8 digits, 0 through 7 inclusive. And then base 16 from 0 to 9, and then from uppercase A to uppercase F. Everything is inclusive. So let's look in practice how these look like. The numeric systems with the various bases, the digits, and then the numbers, which numbers could be a single digit number or a multiple digit number. For instance, in base 10, 4 is a single digit number. 14 is a 2-digit number. Let's start first with the English language alphabet. So the English language has the alphabet, which is with letters A to Z lowercase and A through Z including uppercase. So the letters are A, B, C, D, E, F, etc. Similar to the alphabet in the English language, in these four numeric system bases, there are the digits. So the digits for base 10 are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is not a digit. 10 is a number composed out of two digits. The digit 1 followed by the digit 0. Base 2 has the digits 0 and 1. Base 8 has the digits like this from 0 to 7 inclusive. And base 16 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And since 10 is not a digit, it uses the digit A. B, C, D, E, and F. So this is, as it were, the alphabet of these numeral systems. Base 10 has 10, base 2 has 2, base 8 has 8, base 16 has 16. So the number in base represents the number of digits in the numeral system. Okay. So let's see the first example. Let's look at the simplest number that we'll start with is 0, which is represented identically with the digit 0. So in all four bases, there's a number of one digit, which is 0. What about the number 1 in base 10? In base 2, there's a digit 1, which represents one object. The same thing for the other bases. What about the next one, which is the number 2 in decimal? So that means two objects. How do we represent that in base 2? 0 represents 0 objects. This represents one object, but we need to represent two objects. How we do that is similar to what we do in the base 10. After the last digit, which is 9, will come 1 and 0. So after the number that has only one digit and is the largest one, which is 9, comes 1, 0. The exact same thing we do for base 10. After the number which contains just one digit and is the largest digit, which is 1, will come a 1 and a 0. This is not 10 in base 10, this is 1 and 0 in base 2. This is base 2, this is base 8, base 16, and base 10. There exists the digit 2, so there will be a number with just one digit, 2 in base 8. The same for base 16. What about 3? 3 cannot be represented as a number with just one digit in base 2 because in base 2 we only have the digits 1 and 0. So it will be the next number after 1 and 0. The next number after 1, 0 is 1, 1. 3 in base 8 has the digit 3, so a number with only one digit, which is 3. Same for base 16. So what we can see is that as long as we have one digit that represents that number of objects, we totally use that in any base. So for 1, we could use it even in base 2 because there was a digit 1. But since there's no digit 2, we needed to come up with numbers which have more than one digit. So for all of the numbers that are larger than the list of digits in that base, we'll need to come up with a number with multiple digits, so more than one digit numbers. Let's go at 4. In base 2, there's nothing larger than 1, 1 in the list of numbers with two digits. So this is similar to 99 in base 10. In base 10, there's no larger number with two digits than 99, which means that if we increment by 1 99, we will need more than two digits. So 99 plus 1 is 100, which uses 3 digits, 1, 0, and 0. In base 2, there's no larger two-digit integer, two-digit number than 1, 1. So we will need 3 digits when we increment by 1. So that's 1, 0, 0. Similar to how we went in base 10 from 99 to 100. The same way we go from all of the other bases, from the largest digit to 10, from the largest number with two digits to 100 from the largest number with 3 digits to 1000 with 3 zeros. When we increment with 1, the largest number with that number of digits, the number of digits increases from 2 to 3. All of the digits become 0 except the most important one, the one that's at the left, which will become the not 0 but the next one, which is 1. Okay, let's look at the next. So 4 exists in both base 4 and in base 8 and base 16. So we just write 4, then 5. In base 2, 5 is similar to the previous one, which is 100 plus 1, which is 101. 5 and 5. 6. In base 2, that's 101 plus 1. You cannot increment 1, so this 1 plus 1 will become a 10. 1 and a 10. 6, 6, 7. 7 is the largest integer in base 8. Okay, so 110 plus 1 is 111 in base 2. In base 8, that's 7. We still have a digit. 7, and then 8 objects in decimal. That's there's no larger 3 digits number in base 2 than 111. This is similar to 999 in base 10. That means that the number of digits will increase. 1, 2, 3 zeros, and the 1 at the more important position. Okay, there's no 8 digit in base 8. So after the largest 1 digit number, which was 7, if we increment by 1, we'll get to 0, the number of previous digits, plus a 1 at the most significant part. And 8 exists in base 16. Let's do some more. So 1 and 3 zeros, we increment by 1. 1, 0, 1, 1. So this is not 11. 11 is only in base 10. This is base 8, 1, 1. And this is 9, because there exists a 9 in base 16. In base 10, after 9, so 9 is the largest number with just 1 digit, which means if we increment by 1, we'll get to a number which increments the number of digits. So from 1 goes to 2. Previously there was 1 digit, so we put a 0. We put a 1 at the most significant part. Okay, 1, 0, 0, a 1, and we will add another 1. So 1 plus 1, 1 is the largest 1 digit number in base 2. If we increment by 1, we'll get to a 0, which is like this. So 1, 0, 1, 0 is base 10, 10. Okay, let's look at 10 in base 8. It's just the previous number, which is 9, and then we increment plus 1. The least important digit still can be incremented, so we'll increment that. So from 1, 1, it becomes 1, 2. 9 is not the largest 1 digit number in base 16. So we continue with numbers with just 1 digit, which is A. 11, 1011, 13, and the next one-digit number in base 16 is B. 12. So 11 is the largest two digits number in base 2. So this will become 1, 1, and then 2 zeros. We increment this by 1 and we get this. And we keep what we had before, which is 1 and 3 zeros. One, 4, C, 13, 1101, 15, D, 14, 11. The largest one-digit number in base 2 is 1. When we increment with 1, we'll get a two-digit number. 16, and then E. And the last one-digit number in base 16, which is the value 15 in base 10. 3 ones, and a 0 gets incremented with a 1, becomes a 1. 17, and F. And we'll do one more to get at the first, the smallest two-digit number in base 16. That's, let's put a minus in here. 16, a separator. This is 16 is an important number in base 16. It's the smaller two-digit number. Is an important number in base 8 because it's more than a 4-digit tuple. So that's a 1 and then 4. Like this. Seventeen is so 7 is the largest one-digit number in base 8. When we increment 7 plus 1, we don't get 8. There's no 8 digit in base 8. So we'll get to 1, 0. Plus the 1 will become a 2, 0. And this one, so we get the largest digit, F. So the next one will be the smallest two-digit number, which is 1, 0. Let's put a 17, and we'll probably stop because it's getting very long. But you, with a piece of paper and a pen, should always know, no matter what, even if you forget anything about bases, you totally should be able to write on a piece of paper base 10, base 2, base 8, base 16, make some columns, and on the first position to put all of the possible digits. On the next row, you're going to compute these things. So this is as basic as the multiplication table. You need to either to know it by heart, very advantageous to know that, I know, 9 in base 10 is actually 1001. Very important to know these things by heart. I unfortunately do not know them by heart. So I always take a piece of paper and compute everything. Right? But with a piece of paper and pen, you should be able to invent from scratch this thing which is similar to the multiplication table. It's so basic, it's so important. Right? To know that 14 in base 10 is 1110 in base 2, is 16 base 8, and is E in base 16. Do repeat until you get to the point where, without looking up, without using any tool, are able to compute all of these things you yourself by hand. First step is to be able to compute all of these things, what I wrote in these 4 files. And then you get extra bonus points if you actually memorize whatever is shown right now on the screen. Okay, now let's do some really large numbers. Let's do 143. So this 143 is a 100 plus 40 plus 3. The position in which the digit occurs is important. This 3 will be multiplied with 10 at the power of 0. The second digit the second digit in importance, which is 4, will be multiplied by 10 at the power of 1. And the third in the order of importance is going to get multiplied with 10 at the power of 2. So that's, again, 1 multiplied to 10 at the power of 2, because it's on the third position. So first position, second position, third position. Third position gets multiplied with 10 at the power of 2. 10 at the power of 2 is 10 times 10, which is 100. Plus 4 multiplied with 10 at the power 1, because it's on the second position. So second position gets 10 at the power 1. And then there's 3, which is times 10 at the power 0. So 10 multiplied with itself 0 times is 0, is 1. Anything at the power of 0 is 1. So 3 times 1 remains 3. 4 times 10 is 40. And 1 times 100 is 100, which is this thing, this thing, this thing. If we sum this thing up, we get 143. Similar are the way we go from base 10 to base 2, from base 16 to base 10, etc. Based on this logic that you see in here. That the digit on the position with the least importance gets multiplied by 1 0 at the power of 0. The next digit in order of importance gets multiplied with 1 0 at the power of 1. And the third in order of importance digit gets multiplied with 10 at the power of 2. Okay, so let's see how do we represent 143 in base 2. So that's 143 is, and we need to compute the powers of 2. So we need to compute something like let's go up, lowercase a times 2 at the power of, I don't know, 7 plus b times 2 at the power of 6 plus c times 2 at the power of 5 plus d times 2 at the power of 4 plus e times 2 at the power of 3 plus f times 2 at the power of 2 plus g times 2 at the power of 1 plus f times h times 2 at the power of 0. Which means that the number in 143 in base 2 will be A, B, C, D, E, F, G, and H, where A is something in the vocabulary, in the alphabet, so 0 or 1, B is a 0 or 1, C is a 0 or 1, etc. So all of these individuals, A through H, are a digit in base 2. Okay, how do we compute A, B, C, D, E, F, G, H? By keeping to compute the modulo of, by keeping on dividing by the base and looking at the modulo and the remainder. So let's do that. How do we do that? So 143 is divided with modulo, so integer division, by 2 is 144, that's 7, 2 times 2 plus 1. Let's compute again. So 72 times 2, that's 14, 4. So 144. And plus 1 minus 1. Saying here. So 71 times 2 plus 1. So 142 divided by 2, it's 71. And then plus 1. Okay, and we always keep this one, the modulo. So h is 1. And then we look at the remainder, which is 71, and we integer divide it by 2. So that's 70 plus 1. 70 is 35 plus 1. So the next one, which is G, is the modulo 1. And we have a 35, which we need to divide further. 35 divided in integer fashion by 2 equals 34 divided by 2, which is 114, 17 times 2 plus 1. The next one is F. F is what remains, listing 1. And then we have the 17, which we need to divide further. So that's 16 plus 1. 16 is 8. So the next one after F is E. E equals 1. We need to divide 8 further. 8 divided by 2 equals 4 times 2 and no modulo. Okay. The next one after E is D. D is the modulo, which is 0. And we need to further divide 4. 4 integer division by 2 equals 2 times 2 plus 0. So the next one after D is C is 0. And we need to divide further these two. So 2 divided by 2 equals 1 times 2 plus 0. Which means that the next number after C is B, and B is 0. And then we're left with just 1, and there's no point in dividing 1 by 2. It's clearly that the modulo will be 1, but let's still do it. 1 integer division by 2 is 0 times 2 plus 1. So the next after B is A. A is the modulo, which is 1. The remainder is 0, and there's no way of dividing 0 by 2. Because it will be 0 times 2 plus 0, and this will go on forever. So at the most significant digits, we can have any number of zeros we want. This number 1 and followed by 4 the zeros is the exact same value as this one. So on the most significant position, a 0, then a 0, then a 0, then a 0, then a 0, blah, blah, blah. And then only on the 5th position we have a 1. So this thing is totally identical to this thing. Just as like in the base 10, a 0, 1 is totally identical to 1. If we have only zeros on the most important positions, those can be removed. Now let's prove that this number that we get, so it's the base 2 number A, B, C, D, E, F, G, H, where A, B, C, D, E, F, G, H are one digit in base 2. So that's A is 1, B is 0, C is 0, D is 0, E is 1, F is 1, G is 1, H is 1, and H is the final one. So we actually needed 8 digits in base 2 in order to represent 143. Let's prove that that's the case. We can use Google for that probably. Let's see. Control T. In base 2 to base 10. Google did not learn yet these things. There's probably an online website that can do these types of conversions, but I do not know exactly which of the websites might be. I know that the desktop calculator, both in Windows and in Linux and probably in macOS too, can do these things. So let's try to do that. Let's see, numeral system. Let's switch from decimal to binary, so base 2. No, not binary. From let's use the decimal, so base 10. Let's actually see how they're named in other places. So base 10 is named decimal, numeral system. This one is binary. This is octal. And this is hexadecimal. Okay, so we actually want to go from this value, which is 143, so not 143, but 143, in base 10, which is the decimal numeral system. We want to go to base 2, which is the binary numeral system. So we switch to decimal from this combo box. We go 143, and then no need to switch to the binary mode. It actually automatically computed the binary numeral system value, which is 1 3 zeros, 1 3 zeros, and then 4 ones, 4 ones. And it says that it's in base 2 by putting a small 2 after this number. And it automatically computed in the octal number, which is 217, base 8, and the hexadecimal number, which is 8 uppercase F in base 16. We do that. There are also tables like these ones, but way longer, which then can be used in order to convert large numbers from one numeral system to the other. If we ignore base 10, the conversions between base 2, base 8, and base 16 can be made without doing too much calculations with your brain by using conversion tables. In the sense that if you have the number 11 in 1 in base 16, you take the first one, you convert it to decimal, which this one is 10, which is 16. So you look at 16, 16 in base 2 is this guy, and then plus the 1, which 1 in base 16 is the same thing as 1 in all of the other bases. So you take this one and put a 1, you increment this number with 1. And also this number, when you convert it to base 16, F is many ones. So this last position is actually an F on the least significant digit. So this thing is this thing, and you're going to look it up in the tables, and you're going to see that on line 21 we have F. And then this guy, 1 0 0 1 and 3 zeros, is this guy, which is line 14, which is this guy, which is 8. Like this. So conversions between bases 2, 8, and 16 are a number of times easier to compute than from any of these to base 10 or from base 10 to any of these. So in order to convert from base 2 to base 16, you take the base 2 number and split it into 4 digits like this. This has an immediate conversion to base 16, 20, line 10 to 1, which is an F. And this has an immediate conversion, line 14, base 16, which is this thing, an 8. If you want to convert from base 2 to base 8, we're going to look at this one at 13. So 13 is the, on line 13, we can see 111 in binary, which is the largest number that can be represented with 3 digits in base 2. And so it happens that it's also the largest number that can be represented with just 1 digit in base 8. So we split the binary number in threes, so 3 digits, 3 digits, and 3 digits. This guy immediately gets converted, line 13, it's a 7. When we convert it from base 2 to base 8, the next one, 0, 0, 1, is actually 1, which is this one, line 7, which is this one, line 7. And then 1, 0, it's actually 0, 1, 0, which is line 8, which is line 8, which is 8, 2 in base 18. Let's prove that. So 217 in base 8 should be this value in base 2. We switch to base 8, which is octal, and we write 217, and says that in base 2 it's 1, 3 zeros, and then 4 ones. So now you know how to compute the table of bases up until the 17 objects, and then you know how to convert from each base to each base. You convert from base 2 to base 10 by using this formula. You convert from base 10 to base 2 by continuously dividing by 2 and computing the h, g, f, etc. by being the modulo. What remains you keep dividing. You convert from base 2 to base 18 by splitting the number into 3 digits and then looking at the tables. You convert from base 2 to base 16 by splitting the base 2 number in pairs of 4 digits, and then you look at the table. You convert from base 16 to base 2 in the inverse way. So let's see the number 12 in 1. That's not 12, it's 1, 2 in base 16. So that's a 1 times the largest number in base 16. So that's 1, 0 at the power of 1 plus 2 times 1 0 in hexadecimal at the power of 0. So this is 1, and this is 1 0, which is actually 23, which is actually 16. This is the way you go from base 16 to base 10. So it's 1 plus this thing is 1 0, which is 16. So that's 16 plus 2 multiplied by 10 at the base 16 at the power of 0. So this thing is 1. And multiplied by 2, that's these 2, which is line 8, which is 2 in base 10. Equals 18 in base 10. Okay. And if you want to go to base 2, which is what I actually wanted, is you're going to split the number and convert every digit in base 16 to its equivalent in base 2. So that's 2 on the least important position, which is line 8, which is this guy. And then there's a 1, which is line 7, which is this guy. Let's prove that's the case. In order to use the calculator to prove, you could do the reverse, which is convert from base 2 to base 16. You already have this thing in the table. So 0, 1, 1, 0, which is 0, 1, 1, 0 is this thing. It's line 12 and it's 6. So a 2 and a 1, 0. 2 is line 8, which is 1, 0. 1, 0 with zeros at the front. Okay, and then we have a 1, 0, which is line 23, which is this thing. I don't know. I don't know. Something will come up from trying. The rule is there, but I'm off by 1 probably. So let's go decimal, hexadecimal 12, and then it's just a simple 1 in here. So in converting from base 2 to base 16, we've split pairs of 4 digits in base 2. When going the other way, from base 16 to base 2, you're going to convert each of these into 4 base 2 digits. So this 2 is this guy, but it should be 4 digits, not less. So it's 4 digits. And then this one is this one, but it should be 4 digits. Like this. This is 4 digits, this is 4 digits. If we're going to convert this base to number, we'll get 12 in base 16. Once you have base 2, it's easy to go base 8. You just use pairs like this. So this 0, 0, it's useless when you convert to base 8. And then you have 0, 1, 0, which is line 14, which is 0, 1, 0, 0, 1, 0. 0, 1, 0. This guy. That's a 2 and 2. 2, 2 in base 8. So this 0, 1, 0 is this, which is this, and another 0, 1, 0, which is this, which is this. And this 0, 0 is this, which is this. So it would be 0, 2, 2 in base 8, which is 2, 2 in base 8. So let's see. Base 8, which is octal, and 0, 22. And it's 12 in base 16, 2, 2 in base 8, and 1, 0, 0, 1, 0 in base 2. So this is the theory. You're probably not going to memorize all of this theory without trying it a number of times. Do learn the theory, because sometimes maybe you don't have Google available, maybe you don't have the internet available, maybe you're setting up a data center and 0 computers are alive. So you need to start from somewhere. Maybe you need to compute CIDRs in the networking in local area networks. Maybe you need IPv4 net masks. These things come in handy often. In computer storage, base 8 is not that important, but 8 digits in base 2 are a byte. So this thing is a byte. Has 8 digits in base 2. 1 digit in base 2 in computing can be named a bit. A bit has the only possible values 0 and 1, so it's actually a digit in base 2. 8 bits constitute a byte. The byte is the basic storage type for memory. Random access memory for storage. And in order not to use a long number of base 2 digits, you use pairs of 4 base 2 digits, convert them to hexadecimal, and this makes things way more readable, because this thing is way less readable than its equivalent, which is, I'm not sure what, in base 16. Let's see which number. So 14 is 8, and this thing is the largest one, 21, which is F. So 8F is 1,000 times easier to remember than 8 base 2 digits. Instead of memorizing a long list of bits, it's easier to memorize their corresponding value, but in base 16. That's what we use base 16 for, to make bits more human readable. Thank you.